He joined HASP about a year ago, and you may have seen him in quite a few of the classes. I think he took 40 classes in the summer and fall last year. We were in Florida earlier this year, so we didn't do too much in the fall or the winter. But just a little bit of background on David. He's retired from Spartan Nash as a Senior Vice President and Chief Information Officer. He had responsibility during that time for all business systems, technical infrastructure, and communication technology. He has over 50 years of experience in information technology in retail, wholesale, and manufacturing organizations. Prior to joining Spartan Hash, he held positions in product marketing, technical systems management, and network management for both Hewlett-Packard and General Foods Corporation. He has extensive experience in information technology, communications technology, strategic planning, acquisition integration, and enterprise system architecture. In addition, he's taught classes in communications technology and data center management. He holds a bachelor's degree in business administration and a master's degree in computer science, both from the University of Arizona. And I'm really excited to present you my husband, David.
Good morning. It's nice to be with you all. I'm really impressed that 42 people wanted to hear this talk. I will try not to disappoint you. A little background is Sue talked a lot about my career and whatnot. I am not an electrical engineer. I am not a mathematician. There's an incredible amount of technical detail behind this technology. And I'm not going to, there's a whole lot of things I'm not going to talk about, but it's incredibly powerful technology and it takes a lot for all this to work. And so we're going to talk a bit about that. So hopefully everybody can see my screen. In talking about cellular communications, hold on a second, I got to get control of my, okay, there we go. So what I'm going to talk about today is cellular technology. Why does it exist? Where did it come from? Why is it there? Talk a little bit about the electromagnetic spectrum that is how we electronically communicate on this earth. We'll talk about the history of cellular technology, is what I always call about the G's. The 1G, 2G, 3G, 4G, what are they? Why are they different? And sort of how did they occur over time? Talk a little bit about the carriers that support cellular technology. And we'll, as I do all this, we're going to get into details about what's in Holland and a lot of details there. And then I'm going to talk about 5G. So if you've watched advertisements, there's an incredible amount of promotion around 5G. And so why is that so significant? As usual, in the technology world, we call it the hype cycle. It was come up with one of the research institutes of the hype that goes into technology versus the reality. And so we're going to talk a little bit about what is the reality of 5G and one, why is it so significant? And then what is it really like today? Can you get it in Holland, for example? And then there'll be a short summary at the end and I'll open it up for questions. Normally when I do presentations, I allow questions all the way through the presentation. This is my first virtual presentation. I've got a lot of material, and so if you don't mind, I'm going to wait and hold questions till the end. All right, why is my screen? There we go. Okay, so a little background here to kind of set the stage. This is incredibly powerful technology. It's incredibly complex technology, and it's amazing what it can do for us. But what makes all this possible is the tremendous evolution in electronics, integrated circuits, the powers of computer processors that now you can hold in the palm of your hand. That increasing processing power is what you'll see when we talk a little bit about some of the things that go on behind the scenes, the amount of computing power it takes to make all this work. At the same time that you have all that computer power, it doesn't require a lot of electrical power, and therefore batteries, and batteries are always a big topic when it comes to cell phones. We're able to do this kind of processing and still have reasonable battery life. Oh, and that just reminds me, by the way, if you are expecting me to tell you what the best cell phone is or what the best carrier is in this area, that's not what this topic is about. It's more about how it works. You know, on another conversation, we can go into those areas, but that is not my goal today. The other thing that's very critical to making all this work is fiber optic communications. Fiber optic communications has allowed us to take incredible network capacity and take it out to the middle of a cornfield to a cell tower to be able to deliver that speed to phones and devices that are roaming around in the area or going down a freeway. So that's another critical piece to all this and has really helped the later generations of the technology work. And then the last thing is, and I'm not going to go into gory details about this because it gets quite challenging, and that is the antennas, these cellular antennas. The antenna technology has dramatically changed over the years that allows us to deliver enormous capacity, network capacity out to a device that's going 70 miles an hour down a freeway. It's amazing. And what's coming in 5G, there's major advancements in antenna technology that are facilitating what's going to happen to 5G. So why cellular technology? So we're going to kind of go in, what is this thing and why does it matter and so forth. And fundamentally what it is you have antennas around, around the geography. And if you just had one antenna, and had lots of cell phones or laptops or whatever devices attached to it, you would run into limits very quickly. And with the fact that most of us now have cell phones, the number of cell phones, the number of devices based on the population is just not able to be supported by one transmitter. And so that's why cellular technology was invented. And you'll see as we go through the slides, we divvy up the geography to multiple transmitters to be able to support the enormous number of devices that are out there. And it was a concept that Amos Joel in Bell Labs in the early 60s invented the technology to be able to allow a phone to switch from one transmitter to another transmitter in the middle of a call, not interrupt the call in the middle. It wasn't data transmission those days, but that was a key method, and we're going to talk a little bit about that. Then we're going to talk, and I'm going to show some diagrams. Again, we're not going to get into mathematics because it's incredibly complex. But we're going to show you what the theoretical, what the mathematicians and the engineers look at in terms of a cell. But then we're going to talk about real cells. And we're going to talk about real cells in theory and what it looks like actually in Holland, Michigan. So, so that's a little bit of, so again, this limits of a single transmitter. You have one transmitter and it radiates certain frequencies, and through different methods, these phones can occupy those frequencies and talk to that transmitter, but there's a limit. And so when you get to an environment like today, you just can't support that many devices on a single transmitter. So based on that, we have to divide up the geography and spread it across a bunch of different transmitters, and therefore you have cells. And so these are sort of the theoretical design of a cellular system. Looking at the upper left, you'll see that you cordon off the area. They generally show it as polygons. You cordon off the area and have an antenna, and the devices within that area talk to that antenna. And when they cross over to another area, so say you're sitting in F4 in the middle, and you're talking to that antenna, and all of a sudden you move over to the cell in F3 to the right, you switch from the first antenna to the second antenna. And there it goes. And you'll see F1, 2, 3, 4, those have to do with frequencies. So if you're going to have two antennas talking, the two adjacent antennas typically have to have a different set of frequencies. Otherwise, at the edge, when you're talking between the two cells, there's interference, because on the same frequency, there's one cell phone on one side and one cell phone on the other side. And how does the system determine which of the two? So you can see in what's shown in this diagram that F4, there's no F4s around that cell. They're all different sets of frequencies to be able to keep track of things. So then if you look at the upper right, you see that in rural areas where you're out in, you know, say you're driving along 196 to Chicago or something, or down the west side of the state, and you go by blueberry fields and wine fields and so forth, and there's a cell tower out there, but the next cell tower might be, they might be 20 miles apart, or a cell could be as large as 20 miles across. Where you get to an urban area, and we'll call Holland more of an urban area, then you have to have smaller cells because of the number of people and therefore the number of devices that have to be supported. And then you get to a large metropolitan area like a Chicago or a New York, a large city, and they have to subdivide the cells and make them much smaller because the quantity of devices that have to be supported in that particular area. So that kind of gives you an idea of scaling. And so cells can be of varying size, a maximum of 20, maybe even as high as 25 miles across, when it's where the area is not as dense. So then you look at the left, and in the sort of the ideal theory of a cell is what it is in the middle there, the lower left, where there's circles. But from a mathematical and modeling and engineering standpoint, they look at them as hexagons in terms of how the equipment is designed. But the reality on the right is nowhere near what you see. And when I show you what the cells look like in Holland, you'll see they're dramatically different. So then antennas over time have changed. You look on the lower right, and you'll see that the original antennas were just omnidirectional. So they used to call them sticks, and there were so many, just a pole standing up, and they radiated the same amount of energy all the way around in a consistent fashion. Well, then as we went, that was back in 1G, and 2 and 3G, the antennas became more sophisticated and they became directional. And so you could take a cell and divide it into 3 sectors. And now with LTE, where we are today, you see on the right a 6 sector. So there'll be antennas, and they're aimed in given directions, again, so you can increase the capacity and number of devices that are being supported. So there's cells and there's sectors in cells, and we'll see more of that. So the last piece, sort of on the theory side of things, this talks about that frequency reuse. So over on the right, you see that we've talked about large cells can be anywhere from a half mile across to 25 miles across. Small cells are less than a mile. And then when you're underground in a large city where there's subways or on large high buildings, multi-story buildings, you know, 25, 30, 70 stories, whatever, they'll put antennas within the building and in the subways underground, so that if you're in the metro in Washington, D.C., or you're on the subway in New York City, you still get great cell coverage. And that's because they have antennas sprinkled along the tunnels to be able to support the devices. So then this last thing, and then we'll sort of get out of the theory thing, is over here on the left, you see 4 different cell configurations, and you'll see this little number called FRF, which stands for frequency reuse factor. And so that's in the math in terms of how the engineers design these things. So you look at that slashed cell in the middle, that has a set of frequencies, and these are large cells, and so the grayed out cells are the ones that are running in the same frequency as the slash cell. So they are big enough and wide enough apart so you can manage the interference. When it gets denser, then they'll go to a frequency reuse of 3. So on the one in the center, in the upper center, you'll see the dash line. Well, the cells that are adjacent to it use a different set of frequencies so they don't interfere with one another. So then you see the grayed out cells are at least 1 cell away. And so then on the lower left and the lower center, you see the more extreme case of a frequency reuse of 7, meaning that there's basically 2 cells between every cell that's using the same frequency. And again, it's all about how you manage the interference between the cells. So that's the theory side of things. Let's talk a little bit about what goes on behind the scenes. And I picked two things to talk about. So between that cell phone and the antenna, there's data, there's voice. In the original sense, that's all there was voice. And then there's control signals. And there's two frequencies used. There's one to talk from the phone to talk to the cell tower. There's one from the cell tower to talk to the phone. And so and in today's world, it didn't start out this way, but in today's world, all voice, all communications is converted to a digital form. So it's ones and zeros in digital packets that are being transmitted back and forth. So a little look at what goes on behind the scenes. And again, this challenge of managing these transmissions in these cells. So one, to make a call, so you dial in a number, and somebody asked me, he said, why isn't there dial tone? Well, dial tone never served any function, even on the old landline system. It was just a way for the phone network to let you know that it was ready to hear what you had to say, or to dial your number. So on a cell phone, you key in the number and then you press a button, green button, whatever it is, to make a call. That sends a signal on one of those control circuits or control paths back to the cell tower. It says, I want to call this number. And then the computer systems behind the scenes, which I'm not going to talk about, is a whole lot of complex computer systems behind the towers that make all this work. So they then go off and establish a call. Well, and likewise, if a call is inbound into your cell phone, same message goes out on that control path to say, hey, there's a call coming in. Well, again, to manage this interference, that initiating conversation starts out at the maximum strength of the antenna, its signal coming out to the mobile phone. But once it's established, we want the theory is they want to get the transmission as quiet as possible so it doesn't interfere with adjacent cells. So once the call starts and the voice data is moving back and forth, it measures the error rate of that voice data. If the error rate gets too great, it says, I've got too much power. And I don't have enough power. So what it does is it starts at the highest power and then it starts incrementally reducing the power until the error rate goes up. And then once the error rate goes up, it knows that, okay, this is the lowest power I can go and still have a good signal. Remember, you could be going down the freeway 70 miles an hour and it's doing all this behind the scenes. You have no knowledge. It's constantly measuring the quality of signal and adjusting accordingly. And likewise, a big thing that has to occur is how do you jump from one cell to another? Now, if you're going down the freeway at 70 miles an hour and you're out in a remote area, you could be on a cell and you might have a 5-minute conversation with somebody and never jump cells. If you were in a dense metropolitan area, you're jumping cells all the time or segments within a cell. So how does it do that? So what happens is the cell phone is constantly listening to all the towers that it can hear. It listens, and as it hears different towers, it reports back on a periodic basis. It sends a message to the cellular system, to the towers, to the computer systems behind the scenes, and says, here's the cells that I can hear right now. And here's how strong I can hear one versus another, including the one that it's on right now. And so what happens behind the scenes is those numbers change and the reception and the quality of signal changes from one tower to the next. The computer systems behind the scenes make a decision and say, you know what, it's time to move this device from this cell tower to that cell tower. And so it sends a message out to the phone and says, okay, it's time to switch. And so then they switch cells. Now, we've all had this experience that you're all of a sudden the call drops off. Well, that could be because you got out of range of a particular cell tower, or the handoff didn't work for some reason. And there's two kinds, this is called a handoff. There's two different kinds of handoff. There's a hard handoff and there's a soft handoff. A hard handoff says that I'm losing power from this, I'm getting to the point where I can't hear this antenna. So I've got to make an abrupt switch to a different antenna. And based on those messages, the cell system tells it which one to switch. Or in a more gradual case, it might say, okay, I can hear this tower, but this one's getting stronger. And so the instructions will come out and it'll make a soft handoff where it's maintaining communications with one tower and you're talking or doing your data search or running your app or whatever. And then it establishes a communication with the next tower. And once that's all settled down, then it actually moves the activity. So two different ways that can occur. That's about as technical as I'm going to get, by the way. So let's talk about what reality looks like. So I went in and there's three major carriers in our area. There's AT&T, there's Verizon, and there's T-Mobile and Sprint, and T-Mobile just bought Sprint, so that all becomes one. These are where the AT&T towers are in the Holland area. And I'll kind of highlight a couple of them. The one in the lower left, if you've driven on 196 around Douglas, Saugatuck Douglas, and you're going north and you go across the Kalamazoo River, and then the freeway kind of bends around and there's two very large towers just to the east of the freeway. And one tower is, if I'm not mistaken, is television, and the other, or radio, and the other tower is a cell tower. And so AT&T is on that cell tower. Another very notable one is on the way to Grand Rapids on the east side there, over by the Zeeland Charter Township. There's two towers there. One's a local television station, and the other one's a cell tower. And you can see AT&T Mobility is on that one. My point here is, versus those mathematical models of what cells look like, this is what they really look like. This is because you have to buy land, you have to build towers, you have to deal with zoning ordinance, you have to get somebody to set the equipment up, you have to get the fiber optics out to the tower. There's an enormous amount of work and time and expense that goes into building these things. So that's where AT&T is. Then if you look at T-Mobile, T-Mobile is, you can see they're not on the Saugatuck Tower, but they are on the tower on the way to Grand Rapids in Zeeland. So I didn't highlight the ones that are co-reside on towers with others. Again, this was not trivial getting all this data and getting this put together, so there's sort of limits on time. But anyhow, that's what T-Mobile looks like. And then here's what Verizon looks like. Now you can see Verizon's down on that Saugatuck Tower, and you can also see it's on that Zeeland Tower as well. So my point in showing you all this, one is what's it look like in Holland, and two, it's not the simple symmetrical diagrams that you saw on the theory side of the discussion. So towers get quite interesting. These are more typical towers. You see the one in the lower left is the one that's down by Saugatuck that I mentioned, and there's several carriers on that tower. There's in the lower right, that is a tower that's at 152nd and Lakewood out in the cornfield there, and that has two carriers on it. The couple of interesting ones, well, for us, the one in the upper left happens to be right outside our condo. So we get in Florida, we get great reception in our condo in Florida. And then over on the upper right-hand side, you'll see a newer design pole that the antennas are built into the structure of the pole, and there's a plastic covering it around it, so you can't even see the antennas. So anyhow, those are some examples of towers. Then they also get kind of creative. So the one up in the upper left is out in LA, so it's trying to disguise itself as a palm tree. And then the next one over is actually in Granville, Michigan, by the Granville Mall. Let's see, what is it? Behind the Granville High School. And that's designed to look like a tree. And actually, there's even a better example. If you drive on 131 up north towards Cadillac, there's a kind of a forest that ends by the road, and there's one of these that's just nestled right on the corner of the forest. You can hardly tell it's there. And then on the upper right, you see a couple cell towers that are integrated into power lines, so take advantage of those facilities and put cell towers in them. And then down below, you'll see water towers. Lots of people use water towers. The Holland Township one is at Lakewood by River. And the one, the Holland Charter Township to the right, that is by 112th and Chicago Drive. And it has one carrier on it. The Holland Township looks like it has two carriers on it. And then down in Florida, again, by where our condo is, there's a water tower in there that has a single carrier on it. So people can get pretty creative. And then there's a new thing that's coming out. You're going to start seeing this, and this relates to 5G. And so these are called small cells, and these only radiate for less than a mile. And so, and it's for the high speed part of 5G, which we'll talk about later. And there's a lot of controversy because they're going to have to put a lot of these up because they only radiate for about less than a mile. And so you can see in Holland, there's one at Riley and West Shore. These are called canister antennas on top. There's several of them in Grand Rapids. I found a couple over on East Paris. And then the one on the upper right is kind of a personal one. Our daughter and son-in-law live in Highland Park, Illinois, and they have an antenna. This is a picture I shot from their driveway. So with 5G, they're going to get great reception. But anyhow, there's zoning. There's a lot of discussions with cities about deploying these antennas, and municipalities concern over the quantity of these that are going to be required to do 5G. So then you also have the issue of what happens, like let's say in a golf tournament, that there's nobody out in this golf deal, but then all of a sudden 10,000 people show up for a golf tournament and they all want their cell towers to work or cell phones to work, or even if you're Michigan State or a Michigan fan, and in Michigan you go to the big house and there's normally nobody there, and then 100,000 people all show up and they want their cell phone to work. And so in those particular cases, in those stadiums, they have over time, they started out doing these mobile installations, but they've installed smaller antenna systems in those facilities. So the demand for the cellular carriers to be able to provide service is pretty dramatic and very costly. So then I thought I'd kind of home in on Holland a little bit. So I think everybody on this call probably knows about the Warm Friend in downtown Holland. And if you've ever looked closely, if you look at the east side of the hotel in the lower left there, you'll see 5 cell antennas. If you look at the north side on the back, you'll see 5 cell antennas. And if you look at the west side, you'll see 5 cell antennas. And so these are, through the analysis I did, these are T-Mobile and AT&T antennas. And so to sort of give you an idea what a real cell looks like, I sort of focused in on the Warm Friend so you could see what it looks like. So here is AT&T's coverage from the Warm Friend. And so you'll see that in the colors of the diagrams of the cells or the segments within the cells represent the frequencies that antenna is listening on and transmitting on. So you'll see that AT&T, one of those northern 5 antennas, covers Windmill Island and covers up to Douglas and River on the north side, and kind of the D&W area. And then you'll see there's another cell antenna on the east side that covers sort of the east side of Holland down through Lincoln Avenue, down past about 18th Street and so forth. And then you'll also see a larger concentration in the downtown area because of the number of devices in the downtown area. And so each of these colors represents a different set of frequency, a different set. One is transmitting out to the phone and the other is transmitting back. These are LTE cell segments, or 4G, which we'll talk about a little bit later. But I just thought you would find it interesting to see what a real cell, a real segment looks like, and write it home here in terms of what you see in the Warm Friend. So likewise, T-Mobile, they have some of those antennas as well, and you can see their design is totally different, or not totally different, but significantly different in terms of their coverage. And what I'm showing you is just one cell. So what you have to imagine is there's other antennas that are surrounding here. I didn't take the time because drawing these diagrams was non-trivial. So I didn't take the time to draw it all out, but there's matching towers with matching cells that fill in the gaps. And so that's how they provide the coverage. But my point was to look at those theoretical diagrams. This is what it really looks like. This is what you really experience. And then likewise, Verizon. Now, Verizon isn't on the Warm Friend. Verizon has an antenna that is over adjacent to, on the other side of the railroad tracks from Windmill Island, over by the rail yards. And when I originally designed this map and took a snapshot and started building all this, I didn't have this one in mind, and so that's why it's sort of cut off at the top. But then I thought, okay, the three major carriers in the area, only two of them are on the Warm Friend, and I thought it would be important to show you, okay, how do you get the other coverage? And so this is just another example. So that's a little bit about cells. That's the theory and what they physically look like, and a little bit about the actual radiation of the signal that emanates from the tower. So I want to briefly talk about the electromagnetic spectrum. Again, this can be a very technical topic. I'm not going to get into a lot of detail, but I just want to talk a little bit about the dynamics of the electromagnetic spectrum versus the cellular business. So across the world, the electromagnetic spectrum is governed by each country's federal government. In our case, and in the US, it's the Federal Communications Commission. The key to understand here is that spectrum is a very limited resource. And I'm going to show you, kind of wrap up with one of the diagrams that shows you how it's divvied up. But as technology evolves, spectrum has to get reused. And you probably all remember, I can't remember when it was, 10, 15 years ago, that if you still had an old TV set that was dependent on the VHF channels of 3, 4, 5, 6, 7, 8, 13, that you had to figure out a different way to get the signal, because all those transmitters that remained in that spectrum were going to get shut down. So most people were running on cable TV by that time. Digital TV had come out, which uses a different part of the spectrum. And so they finally just forced us to say, hey, it was going to waste. And because it's such a valuable commodity, they had to free up that spectrum. So I'm sure everybody probably remembers in one fashion or another when this happened. And so that spectrum got freed up to be reused in the cellular business because the cellular demand was just so great. And it's not clear to me when we go through the generations and we talk about how this has all evolved, that everybody understood what a dramatic growth and evolution that this technology was going to go through. So in the US, spectrum is now auctioned off in a bidding process. And I'm going to show you a little bit about the bidding and the amount of money that got spent, because it's amazing. But if you win a FCC auction and you have spectrum, you have 12 years to use it. If you don't use it within 12 years, you forfeit it. It goes back to the government and can get resold to someone else. Whole companies have been purchased not because of their intellectual property or anything else, just because they had rights to a given spectrum. And so maybe they wound up with spectrum through some divestiture, or they won it in an auction. They had some cool idea to build something and it didn't work out. And so then the corporation's just sitting there and one of the big guys comes in and buys them up to get access to that spectrum. So again, I'm going to show you some kind of simple diagram. So the electromagnetic spectrum, the one I've got several slides here, some different pieces of the same thing. So the electromagnetic spectrum goes all the way down to AM radio, which is very low frequency, and goes all the way up to gamma rays, radioactive elements, X-ray machines, and so forth. And in the middle is the spectrum that our eyes are sensitive to. And so that is what the visible spectrum is. And so it just so happens that humans' eyes can see that part of the spectrum. And so anyhow, just so you understand the whole breadth of the magnetic spectrum, part of it is visible light. So then if you look at it from a different point of view, this is the wave that's shown in the middle is a sine wave, and based on the frequency of that wave, it completes the 360-degree cycle slower or faster. And so the waves are very small and oscillate very fast on the far right-hand side, and they're very large, and like they can be wider than a building. They could actually be, in some cases, if the frequency is low enough, a mile. It takes a mile for that signal to make its full cycle. And so down in the middle there of the diagram, you'll see sort of an analogy of size of the frequency and how big it is compared to an atomic nuclei, a honeybee, a human, a building, etc. And the other thing to understand is in the lower frequencies to the left, that can permeate buildings, waves, the earth, and so forth. Whereas the stuff on the upper right, it doesn't go very far. And that plays into the cellular design. So homing in a little bit on communications related stuff of the spectrum. So from about 3,000 hertz down at the bottom there, and that's 3,000 cycles per second of the wave, all the way up to about the 30 gigahertz to the far right, meaning that oscillation is occurring 30 billion times a second, very, very fast. You can see that, and because of the penetration, maritime radio and so forth, where there's long distances involved and getting over the curvature of the earth, having a signal that can penetrate a lot matters. And then you see AM radio, shortwave radio. The area we're really talking about is VHF, UHF, and SHF, which are where the spectrum is that cellular operates. We talked about getting rid of VHF TV to free up that spectrum for cellular, and satellites communicate in the higher end and so forth. Wi-Fi, all those things are in this range, and that's kind of where we're talking. So again, I'm not going to go into a lot of detail here, but I wanted to put this chart in to show you, if you took that entire spectrum from 0 cycles per second at the upper left and 300 billion cycles per second in the lower right, you do basically take that strip of transmission and cut it into 7 equal segments. This is what a chart looks like. And this chart is published by the US government. This is a 2016 chart. The point here is, the only point I'm trying to make is, look at how the spectrum is divided up for so many different uses. That's the whole point of why it's so valuable and used by so many different things, whether it's satellite communications. You can see the big blue areas are broadcasting in that second bar. They take up a lot of space, and so there's just a huge demand, and the spectrum is divided up a lot. So managing that spectrum is no easy task. And then finally, I just wanted to talk about auctions. So back in 1997, there was about 300 megahertz of spectrum that was sold. It was up in the 2.3 gigahertz range, and it sold for $13.6 million. So wireless goes crazy, demand goes crazy, and then you're in 2008, and a piece 3 times that large sells for $14 billion. In January 2014, a small segment, or a small piece of 10 megahertz of range in 2 segments, 2 pieces, sold for $1.5 billion. So it wasn't very much, and it came in 2 segments, and so it wasn't worth a lot. Versus 65 megahertz of range, a lot of capacity, in 7 segments, or unfortunately, but in 2014, it went for $41 billion. This stuff is incredibly valuable. And then the latest in July of this year, there were 3 ranges up in the high end. They didn't sell for quite as much. I don't mean to make it sound like 7.5 billion is not a lot of money, but the point is, it's up in that high speed range. It doesn't penetrate as much, so that's good for high speed communication, but it has limited use. And so anyhow, I just wanted to kind of give you a little bit of a flavor of what people spend for the spectrum to buy it and to be able to support these networks. So let's talk a little bit about the history of technology, of the cellular technology. The objectives and you'll see, and the goals for this technology changed a lot. We're going to talk about the different generations. And the key thing to understand here is smartphones changed everything. When Steve Jobs came out in 2007 and introduced the iPhone, and I'm not saying that the iPhone is the best, but that was the one that really created the model that governs our use today, and we'll talk more about that. So different generations, they roughly come in decades. So the first generation started in 1970 and went through the 80s. 2G was in 1990 and lasted most of that decade. 3G 2000, 4G, and 5G is now just starting. My point in all this stuff is it takes a long time. It takes a long time to build the infrastructure, to build the towers, to lease the space. It takes an enormous amount of money. It's a huge investment. And then they have to convince us as customers to buy the stuff. You know, is somebody going to buy that cell phone, and how much are they going to cost? Now, cell phones have been pretty much they believe that we've sold. In fact, I think there's some statistic, I didn't put it in the presentation, that shows that there's more cell phones than there are people. That's not actually true, but a number of people have multiple phones. But my point is, they sort of feel like they have saturated the market with cellular phones. Part of that, you see, we pay the full boat. We pay the entire cost of the cell phone today, where it used to be subsidized by the carriers. The reason it was subsidized by the carriers is they were trying to get more subscribers. Well, the subscriber growth is not very significant now. So now we have to pay the whole price of the phone. So anyhow, this technology, it's an enormous cost. It's enormous to get the customer to change when they do an upgrade from a new technology to, for example, from 4 to 5G. You know, when's everybody going to change their phones? It's going to be a while. And the technology gets refined during those decades. So they come up with different ideas. The engineers, you know, they do their experiments and they do their hypothesis and so forth. And they come up with changes to the technology that allowed it to squeeze more data to get more performance out of the existing infrastructure. So anyhow, so it takes a long time. So let's talk about 1G. It wasn't called that because they didn't know there were going to be generations yet, but this was an analog system. It was in use in the 70s and 80s. It was a very small number of people that used it. It had a data bandwidth of about 2,000 bits per second. Now I'm going to talk about data bandwidth and all this. And so I ask you to think about your internet access that you have at your home or wherever you live. And so some people have 10 megabits, some people have 40 megabits, some people have 60 megabits, some people have 100 meg. The carriers are always, or the cable companies and AT&T, the communications folks, are always trying to sell more speed. But as I talk about these speeds, think about the cellular speed that you're, the cable and internet speed that you have in your home to kind of, so you can kind of see what's going on here. So voice was all FM modulation. In other words, it was just an analog signal like old style phone lines. The RF channels were about 30 kHz. That was about how they did it. They used it, and I'm not going to get into a lot of details because this can, you know, this is several classes. Frequency division multiplexing, meaning it's like on your TV or on your FM radio, from tuning in one channel to the next, you're changing frequencies. Same thing with this. In order to get to a different conversation, they would change frequencies. And so the primary service was analog phone calls. And the phone that you see in the lower right, typically you saw it was probably a wealthy person that had one of those, because the common individual didn't typically use these, or certain businesses, but it was very limited use back in that day. So in 2G, that was around 2000 or 1990, basically the 90s. They had converted to digital technology by that time. In other words, the analog signals were converted to bits, and data bits or packets were sent back and forth. The core network was still very analogous to the public switch telephone network. The data rate, they could compress or they could convert your voice into about, the common was about 14,400 bits per second. Again, think of your speed of your internet access at home. The voice was digitally encoded. There was a variety of different RF channels that were used in different parts of the spectrum. There were primarily two technologies. GSM was a, excuse me, a technology that was European cell phone manufacturers tried to come up with a standard, and AT&T in the US adopted that standard. What I think the predecessor to Verizon or Altel was using CDMA as their method for how to encode this data into those frequency spectrum. And you can see there's various types of multiplexing. I'm not going to go into the details. One is frequency, one is time, and one is carrier. And so it supported digital phone calls. There was very rudimentary messaging, nothing like what goes on today, but that was the first time any sort of messaging capability showed up. And you can see an example of a phone from the day. Then there was the third generation. The third generation was from 2004 to towards the end of 2010. It was all digital. The core network now is packet-based. Data rates, and this is funny because I'm going to talk about the theoretical data rates, again, going back and thinking about your internet coverage at home. There was a technology called EVDO that would allow them to do 3 megabits, and then high-speed digital packet access, I think is what HSDPA stands for. And again, it's a way to encode the data in that frequency spectrum. That could get up to about 15 megabits, but that was later in this time frame. Digital was encoded, various frequencies and the various multiplexing techniques and so forth. But now we have digital phone calls, so the quality improved, by the way, and all of a sudden messaging was occurring, and with the introduction of the iPhone, data and apps became a thing that didn't exist before. And you'll see in the lower right there's a BlackBerry, which if you were in the corporate world, BlackBerry was a very prominent network and device that was sold. Well, the company exists now, but not anything like what it was. But anyhow, the point is we're moving beyond just a phone, and we're truly doing messaging and data in the third generation. So this is where we are today, by the way, 4G LTE, which is probably, if you've looked at your phone, you've probably seen that nomenclature. I'll talk a little bit about that in a minute. It started in 2010, all digital. Now the whole thing is based on internet technology. Your phone is nothing more than an internet device on an internet service that's provided by AT&T, T-Mobile, and so forth. And so they're just moving packets around. The theory of the technology allows them to go at about in the hundreds of megabits. The theory will tell you that it can do 300 to 400 megabits. I'll have a chart later that shows you what reality looks like. In voice is all done voice over IP. You may have heard of this technology, but it's where, again, you take voice and you turn it into bits or data packets, and there's a very standardized voice over IP standard that everybody supports. And so your voice conversation coming off your phone just looks the same way as it does your internet access. It's just data packets. The RF channels were wider. They used a more complex multiplexing, which again gets into serious math and a couple courses by itself. So the primary service now is all IP. It's phone calls, but now messaging and data really are the dominant users of this technology, or the dominant activity going on cell phones today. I always joke, they make great computers, and by the way, they are a phone. And so it all depends on how you use them. And then 5G. 5G is just, even with all the hype, you know, you can kind of ignore the hype for a while, and you'll see why in a few minutes, but it started, the rollout of 5G started in some large cities in 2019. It's all digital. Again, it's internet-based, it's IP-based, and it has a very flexible and a huge data rate goal of 20 gigabits per second. So an enormous amount of bandwidth. Again, the voice is over IP, and then RF channels, they're generally wider, and there's two sort of groups, the way I like to summarize it. There's the group that's down in the frequency range that we're accustomed to with cell towers today, and there's this what's called millimeter wave, which is the really up on that spectrum in the 20 to 40 gigahertz range. If you remember from our earlier discussion, those waves are very fast, and they don't penetrate well, and they don't last very long. And that's why I showed you the pictures of the small cells, because in order to get the super high speed that they'll all market to you, they've got to put those canister antennas in neighborhoods to be able, because it won't go much more than, you know, less than a mile, a half mile or so. So they'll put it up on light poles. You'll see them in different places. There's a couple of them in Holland right now, but they aren't all operating. But it's going to take them a long time to deploy that kind of technology. So in the traditional range of 5G and about the traditional frequencies, they've come up with more creative ways of how to move the data. So it will be higher performance when it gets there, but nothing like the super high speed stuff that you'll hear them tout a lot. So again, the multiplexing, not unlike LTE, only if there's some further refinements of it. And the primary speed is high speed, high capacity, and lots of different services. And we'll talk about what that means in 5G going forward. So here's an example. So you talk about all the theory, here's reality. And so there's an online resource called Tom's Hardware Guide. It's now, I think, just called Tom's Guide. It's been around for 20 years, and they're really good at doing analysis of communications and computing hardware and so forth. They did an 8-city test last year and looked at the performance that you actually see on your cell phone or on your device, laptop, whatever they used, in those 8 cities. And you'll see Verizon in this particular set of tests came out the best at 53 megs. Even though that technology will support 300 or 400 meg, it's only doing 53, probably not unlike the internet service you have at home. And the upload going in the opposite direction is about 17 meg. AT&T and T-Mobile were pretty similar at about 37 or 36. And then Sprint was quite low. Now, T-Mobile has been purchased by Sprint, so they're going to get all those cell towers and infrastructure, and so they'll be able to improve with that consolidation and that investment. But this is the reality of kind of, you know, you can talk all the theory all you want, but here's what the reality looks like. And then the other thing I thought I'd throw in is, if you look at your phone, and everybody has a different type of phone, but there's some games that they play, and so let's talk a little bit about it. So you say, oh, I've got 4 bars, and I've got a great signal. Well, what those 4 bars tell you, and there's been lots of debates in the technical side of the industry, it doesn't tell you everything. It says that I can hear that cell tower really well, but it doesn't tell you the quality or the contention. And I use the example of, if it's in the middle of tulip time and you're in downtown Holland and you whip out your cell phone, you'll see 4 bars, but the likelihood of you being able to do anything is probably quite low, because the other 5,000 or 10 or 100,000 people that are lining the streets are all trying to do the same thing. And those cells that you saw earlier that are designed for normal use aren't prepared for that number of people all trying to use the technology. So the bars can be deceiving in terms of the quality or contention. Older phones, there's not much 3G technology left, but you might see 3G, and then you'll see 4G, and you'll see LTE. Now, LTE is the real thing, if you are in other countries and you see 4G, then it's the same as LTE, the fourth generation. But in the US, they play games. And so in the US, it's actually an enhanced version of 3G. It's not really LTE, it's not the fourth generation. It uses this technology, I mentioned it earlier, high-speed data packet access, that allows it to go faster than traditional 3G, maximum of 42 meg, but it's not the LTE standard. And the other thing is some vendors are playing a game, and you'll see 5GE. Well, 5GE isn't really a thing. It's not 5G. It's more like, I would equate it more like to 4.5G. In other words, it's using LTE technology. It's an enhanced version, but it is not 5G. And then 5G will be true technology. And the standards folks are debating right now about, they'd like to have a 5G, or the carriers would like to have 5GR for 5G, it's a reliable connection, or 5G fast, it's a fast connection. But the standards bodies haven't agreed yet, and so there's still debate on those two, but we may see those going forward. So I'll talk a little bit about the carriers. So initially, when in 1G and 2G, there were two carriers, what was called wireline and non-wireline. Wireline were the same carriers that were provided, that was phone company basically that provided phone service. And non-wireline was the new guys that came in and were just doing cellular. So there's a huge amount of growth. And then there's been a lot of consolidation as the vendors consolidate to get a national presence. And so a lot of the larger carriers purchase smaller carriers to get, one, their spectrum, or two, get their towers so that they could build out a national network. And so now there are three major carriers. Verizon, the same three I talked about earlier, AT&T, Verizon, and T-Mobile. So you may hear about other things. So there's resellers. So again, at the top of the chart, you'll see the four companies that have, and the T-Mobile and Sprint being combined, now three companies that have the physical infrastructure that we all run on. But you'll hear consumer cellular, for example. Consumer cellular is advertised on TV a lot. And so they run on AT&T's network. So they cut a deal with AT&T and they're selling you a service. And it may be a great service. I'm not being critical of any of these folks, but they don't actually own the network. AT&T is running the network for them. And in some cases, a couple of these folks are actually owned by the carriers. One of the things I noticed, I just made a change, breaking change, is I saw ads on TV for Xfinity, or what used to be called Comcast, and Spectrum, which used to be called Charter. And those are both carriers that are in the area. They're cable providers. And they talk about selling wireless services. Well, they're a reseller also, and they're reselling Verizon's network, and they're reselling, in both cases, they're both selling Verizon's network. And so just so you know, when you're talking to these different folks, and again, you may have all seen these different track phone. Those are kind of more disposable type phones and so forth. So anyhow, there's lots of names out there, but the fact of the matter is now with the acquisition of T-Mobile and Sprint, there's really three major carriers that have a national presence. And I'm not going to go through this detail, but you might say, you know, where did AT&T come from? Well, AT&T was the original Bell Telephone Corporation, born back in 1877. You'll see in the upper left-hand corner, and then they were broken apart in 2084. And then and actually, if you saw a detailed chart like this, you would be amazed at all the different companies that have been sold and resold and purchased and so forth. But over on the right, now this chart was from the latest one I could find was from 2013. You see AT&T. You see Verizon, you go down to the lower right, you'll see T-Mobile, and you'll see Sprint, CenturyLink. I think CenturyLink was purchased by Verizon, and Sprint now is purchased by T-Mobile. A little background, Sprint, so some of these places have long history. Sprint came out of a network that the Southern Pacific Railroad built a microwave network to support their operations. That eventually became United Telecom, that eventually became Sprint. So all these have long heritage. MCI, Robert McGowan was very famous, a guy that led MCI and helped break up the phone system. GTE was down in, over on the lower left, was a carrier down in Saugatuck. Actually had a long presence both up in Muskegon and the Western Michigan area. So a little bit about their history. So there are about 60, almost 70 wireless carriers in the US, but most of them are regional carriers. So there's one in Alaska, and there's one in Wyoming, and anyhow, there's lots of small folks around the country. But there are three that have national coverage. Verizon Wireless has the largest at 151 million as of late last year. AT&T basically has the same number. They're both sort of neck and neck, if you will. And now that T-Mobile has bought Sprint, they're up to 86 million. So of the three, they're the smallest. But again, it's all about the national coverage. It's about having that infrastructure and being able to leverage the technology. So that's a little bit about the carriers. So the last thing I'm going to talk about is why is 5G so different? And so I mentioned a little bit about the impact of the smartphone. We'll talk about that, talk about some of the apps that people run. There's been huge growth in demand, but as the technology evolved, the carriers and the folks in the communications industry dragging fiber down the street to everybody's house and doing all those things, they really designed 5G to be a communication utility. It's not just designed around the cell phone. You'll know it as a cell phone, but there's a whole lot of other things that are going to be running on 5G. So it's designed to support many, many needs. Supporting a phone is just one of its many services, and that's part of the big deal. You know, with all the hype, the real big deal in the communications industry is what this is going to do for our society long term and the technology to service. And as I said, the smartphone changed everything. So think about this: when the phone came out, it was just for making a phone call. Well, now look at how much activity goes on with text messaging. You can browse the internet from your phone. You download and run apps. There's millions and millions of apps. You check your email. If you're active in social media, you might be posting on social media. Some people play games. And that, by the way, that's not just young folks. There's a guy I work down in Florida, and he's like 72, and he's like a major gamer. It's not my thing, but it's a very popular thing to do. And then you're walking down the street and you can watch a streaming video. You can watch a news program, or what happened on a late show the night before, or a concert. I mean, you can just see anything. And look at the number of people that use their cell phone when they're out running to stream audio, whatever they want to listen to, it's all coming through their phone. So when something was designed for a phone call, has evolved dramatically with the advent of the smartphone. And so here's an example, and I just thought this was an interesting thing. If you look at what people spend their time on their phone with, their, if you will, the digital time of using various apps, like the number one thing is people using maps. I live and die by Google Maps, text and messaging, listening to music, doing photos. Gee, what happened to the photo industry? Now your cell phone is photos, and moving those around and storing them are all facilitated by the cellular network. Checking weather, another great resource that everybody uses all the time to check the weather. Games, if you're into gaming, personal use, social networking, retail. Now I came from bricks and mortar retail, but I will tell you that Amazon is an app that I have on my phone that, and I'm very, very serious about going to bricks and mortar retail stores whenever I can. But for that obscure stuff, I'm happy to fire up Amazon and request something that I want. News and information, sports, portals, politics, and so forth. So there's just a whole lot of uses that apps have generated that never existed before. And the growth in demand, this is from Ericsson, they're one of the major cellular equipment providers, just looking across the world at different data traffic, how many gigabits of data are moved, or gigabytes of data are moved every month over the course of time. And you can see in what they're projecting in 2022, if 2021 or 2020 were on this chart, they would be very close to what you see in that large bar. So with that cell phone, a lot of needs, communication needs evolved, and one was high performance gaming, augmented reality. The idea in Google Glass wasn't very successful, it wasn't, but it will continue, where you wear a pair of glasses and you're looking at the space around you, and the computer systems are analyzing that and providing information, like you're into plants, and there's there's a plant app that I use to identify plants in our yard. And if I was in augmented reality, I'd be looking out the glasses, and a little line would come up and say, well, that's a hosta, or that's a oak leaf, just different types of plants. And then there's IoT, the Internet of Things. And a perfect example, I'm going to show you one specifically, is electric and gas meters. So people used to come around and read your meter. Boy, wouldn't that be great if you could convert that all to use the network. Appliances, how many people have refrigerators, LG or Samsung refrigerators that are on the internet? Or you have a washer and dryer that are on the internet. The number of devices, our sprinkler system, the controller for our sprinkler systems on the internet. And then traffic systems, controlling all those traffic lights, and then autonomous vehicles. As we talk about cars and devices that are moving autonomously, they need serious communication capabilities. So as I said, look around your house, there's just an awful lot there. So 5G is designed as a general purpose communications utility. A phone is just one piece of it. They want to support all the things we just talked about. So there's many different communication services provided. Super high speed, low latency. Latency is a term that describes the amount of time that it takes the signal or the data to get from its source to its destination. And so if you think of an autonomous car, and if a car is getting some update of some information, you want that stuff to get there quickly. Or gaming. Gaming requires very high speed response. When 10 people are playing a game and they're all located in different places around the world, they have to get information back and forth very quickly. So supporting a phone is just one of many services. It serves a lot of needs, and that's the idea behind 5G. And so if you look at the vision from the visionaries that are putting together 5G, they look at this triangle or tripod of the top being super high capacity and high speed, the lower right being ultra reliable and low latency communication. In other words, it occurs quickly. And then on the lower left is computers talking to other computers, whether they're appliances, cities, whatever. And so you can go down, I'm not going to go through them all, but you see in the upper right, if you had a 3D TV or ultra high definition TV and you didn't want to connect it to the cable system and you just want to deliver it by 5G, well, it requires a lot of data, but it has to be pretty reliable. Industrial automation, self-driving car down on the right, health systems. You can see in the center, there's the voice. Doesn't have extreme requirements in any case. But then all those devices that are in your home that could possibly be on the network, you can see those in the upper left, and then traffic control systems, industry, various other functions in the lower left. So they have a very broad vision of what they're trying to build here. And I use this as an example. I don't think BPW does this, but if you're a consumer's energy resident or customer, and we are, we live on the north side of Holland in the consumer's energy region. They went through a few years ago and replaced all the electric meters with this General Electric model meter. And that uses cellular communications to report back to consumers through the nearest cellular tower hourly usage data every day. So at the end of the day, It says, well, this particular resident used this many kilowatt hours in hour 1 and this many kilowatt hours in hour 2, etc., throughout the whole day. And so if you go to the Consumer Power website and get into your account and look at your information, you can see what your daily draw was, you can see what your hourly draw is, and it's all done electronically. They don't have to dispatch people to go read messages and so forth, read meters and so forth. And likewise, power loss, and sort of the last hope's gone. There's a little bit of a battery in there, and just before you know, a storm came through here a few weeks ago, and we lost power. Actually, we lost power for a little over 3 days. The last thing it does is it sends a message off to consumers and say, hey, this lost power. Well, if you think about it from a consumer standpoint, you know, the way they used to depend on determining if there was an outage was based on phone calls. Well, now they know immediately what residents have lost power, and from that, based on their network design, they can look where the common location is and dispatch people and get resolution quicker. It still may be a lot of work to get there, but they can get to the solution much quicker. And they attempt to, whether it's right or wrong, they attempt to indicate how long it's going to take to restore it. But here's a perfect example, and also Consumers has the same thing for gas meters. They deployed a system. We don't have our gas from them, but again, this is just a simple use that's in existence today. This is using a 4G LTE network. This isn't 5G dependent, but you can extrapolate these to many devices that are around us. So the 5G infrastructure, I've kind of already talked about this, and there's a low band that's a traditional cellular frequencies. It's not a major increase in speed, but they're playing with the standards, and it is better. Range is similar to the past. They're traditional cells, more or less like what I showed you. Some other nuances, but and then there's the hot narrow band or the super high frequency stuff. It's a major increase in speed. Very limited range, as we've talked about, and it requires a lot of increase in antennas, and we saw some of the small cells there. And here's kind of an example of what the 5G technology, with the super on the right is 5G, on the left is 4G. So you see the range of a cell or a segment on the left, and on the right with these super sophisticated antennas now, they can target the beam and the signal that goes out to the given device and give it a slow speed, give it a high speed, change the latency. They can control the signal come to you. It's called beamforming, that allows it to deliver the kind of service that is needed for that device. For example, electric meter doesn't need a lot of service, needs a relatively slow connection and doesn't require a lot of capacity. So they can customize the communication to the given device. Standards are still being developed. This just came out 2 weeks ago. It's release 16 of 5G. I'm not going to go through all the details, but they released a whole lot of increased specifications and design information about where 5G is going to go and how it's going to be used for different devices. So the reality, it's only just, in terms of 5G, it's only just begun. It's available in a few large cities. It's very expensive to build out, and upgrading existing towers, large effort to deploy those small cells. In West Michigan specifically, in Grand Rapids, they will have low band service late this year. Holland, they are anticipating, what they told me is mid 2021. Obviously COVID has delayed some of this, but that's what they're currently saying. Verizon will have selected Grand Rapids locations and GVSU, because of where the kids are, low band in 2020, and then Holland in 2021, again, low band. And T-Mobile's been a test market for 5G, so they've actually had the low band version of it available. But again, the phones aren't there. Apple is, again, I use Apple, we happen to be an Apple household, but Samsung has a few 5G phones. I wouldn't get a 5G phone right now, maybe next year, but the standards are still evolving, and so there's going to be a lot of refinements to come. So that's kind of my whirlwind tour of cell phone technology. Again, trying to keep it at a high level. It's been an amazing evolution over 40 years. Smartphone has been a huge influence. And like I say, it was kind of a seminal moment. Not that the engineers and so forth didn't have these ideas before, but it really changed the perspective in terms of the population at large and how we use things. 5G as a utility will dramatically change things over time as it evolves. Again, the time to get this stuff rolled out is not trivial. A lot of expense, a lot of work. But the general feeling is long-term, wireless communications will be the norm. So your cable access, your phone system, the kind of stuff that gets delivered to your home, the vision is long-term is you will do that all via 5G or some form of wireless communications. How long will it take to get there? Don't know the answer to that, but because we're just in the beginning, but that is sort of the long-term vision of the engineers and the companies that are driving this. So anyhow, I hope this was informative and useful for you. I'm happy to open up for questions, and I will try and answer what I can.
I have a question for you. If you, one of the many uses for for an iPhone is banking, and I'm wondering how secure the banking data or any data that's on an iPhone is, as well as how secure is Apple Pay.
So that's an excellent question. There's an enormous amount. If I showed you a couple different things. One is if I showed you the computing environment that supports all this, one of the major subsystems is the security system, keeping this stuff secure. So all the communications is encrypted as it goes back and forth between your phone. So it's not like somebody can just hop on a communication device, and they might be able to see data coming back and forth for your phone, but they can't understand it. And so the banks have actually been, they're a very cautious group, having been involved in retail and running a payment system that processed about 30 million credit cards a year. Security is near and dear to my heart and those organizations' heart. So there's an incredible amount of encryption and technology that goes in to using, to supporting the bank applications. So me personally, I feel very comfortable that the security is there and is not a concern. Apple Pay, the other thing about Apple Pay and there's Google Wallet. I'm going back to my working days and trying to remember all this. Anyhow, how they actually implement that is your credit card number is not flowing around the network. It's a what's the word? A token. It's a different number that is associated with that particular transaction and relates to your credit card, but your credit card is not moving across the airwaves. It's back on a computer system elsewhere. So I would tell you that the security is quite good. So and somebody who would have gotten to go to jail if I always joked about this when I was at Spartan, because again, I ran a payment system for 22 years, and I always joked that I wanted to retire on my schedule, not the board of directors schedule, if I ever had been hacked. So I feel very secure about it. You should too.
Thank you.
Dave, Bill Wells, a great presentation. Question, I have a brand X carrier track phone.
Yes.
And I know that they use all three of what will become three major carriers.
Yes.
How do they pay for that? Do they pay for it by the bundle of data, or do they rent by the month, or how?
That's a good question. And I don't know the details of those negotiations, but I would guess that they pay by some number of subscribers and the amount of data that's moved. And I'm sure it's very attractive pricing, but I don't know the details of that side of the transaction.
Thank you.
I had put a question in on chat, but it didn't come through, I guess. Is there a reason that when I go into the north side into the Holland Township area, I can't get internet communication? Is it because I'm on AT&T and they're on Verizon and there's no crossover there, or what's the deal?
So what I would tell you, and does it change from time to time, or is it always that way?
Well, I go.
In other words, when you're in the north side of Holland or whatever, does it always not work, or just sometimes doesn't work? You must be muted. I can't hear you.
And how to do everything. And so I said, well, I give up and I'll just go home and do whatever I want to do there, and I'm fine. But I couldn't use a lot of things that I needed to be on, have an internet connection on.
So it's hard to know without seeing more information, or without knowing more information. But I would tell you that what I would expect would be the case is that you're either in between a couple of cells, or you're in a bad location with that kind of coverage. It also could be, I don't know how current your phone is. In later phones, the antennas get better. Anyhow, there's a whole lot of things that can play into it. So it's hard from this standpoint to be able to answer that question. I apologize.
I have a question about the difference between cell phone wireless technology that in the United States and satellite phone systems that seem to be more prevalent in Europe and in Africa. I know in 2011, when I was visiting Sierra Leone, I bought a cell phone there, and I was able to call the United States and have a much clearer conversation with my husband than my husband. If he called me, it was not a good connection, but if I called him, it was a great connection.
So a couple things about that. So it's sort of the curse and the benefit of a technically advanced society. So in the United States, phone systems, cellular systems were developed in sort of the infant stage, if you will. And so they were like 1G, for example. 1G never occurred in Africa. 2G never occurred in Africa. They started out and in that country, because dragging wires to different places in those countries, dragging wires to where we had communications technology years ago, they didn't. And so cellular systems in other countries, and particularly in Africa, that's one of the primary ways they communicate and the way they do banking. And so I'm not surprised that you would be in certain areas and the coverage and the quality of signal would be extremely good. Now you mentioned satellite. If it looked like a normal cellular phone, it still was probably running on a cellular system. A satellite phone is typically larger and has a kind of a stick that sticks out. Those systems were again developed for parts of the world where cellular coverage was not very good or hard to implement, like in the middle of a desert or whatever. And so satellite systems do exist, and they tend to be quite good. They're very expensive. But the example I think you're talking about was cellular coverage in the African continent, and it's actually quite good. I can go on I can tell you a lot about the evolution, the history, all that stuff, but I suspect that's why you had that kind of experience.
Dave, when I use my track phone,
Yes.
Am I actually, even in a single call or a single session, am I using multiple vendors, or if it starts with AT&T's towers, does it stay with AT&T? I should say antennas.
It starts with AT&T antennas, and then where you're going determines whether you're staying on AT&T or not. If, for example, if you were to call me, for example, you would be on an AT&T antenna. If you were to call my cell phone, I'm an AT&T subscriber as well, so it would never leave the AT&T system. If you called a friend that had a Verizon phone, it's going to start out on the AT&T antennas, get back in the back with all the computing systems, and then get routed around and come out on a Verizon antenna to talk to the person that has that cell phone. Does that answer your question?
Yes, it does. Thank you.
Yes.
Dave, with the increase of cellular communications during the pandemic, and let's say, for instance, if the schools nationally decided to go to online education, right? What's the threat to this whole system breaking down?
Oh, capacity?
Uh-huh.
Well, that's a thought-provoking question. I suspect, so when the engineers design these things, they design them with a margin, a growth margin. And I would suspect to support that effort, because most people, I mean, you have the folks that don't have access and how they choose to support that. In the case of West Ottawa example, they deployed buses with wireless connections for the people that didn't have access, so they could bring their laptop and sit in the parking lot and interact with the school system through that Wi-Fi. I suspect the system is large enough to support that. I would be surprised that, again, with the mobile cell towers and so forth, I would be surprised if it would be an issue. It's a good question, but I don't think it would be an issue.
My good friend Elon Musk has already launched several hundreds, I think, at least dozens of satellites that he ultimately plans to provide cellular communication via satellite for the entire world.
Yes.
And it ultimately will require thousands of small satellites to do that.
Yeah, they're putting them up at 64 a crack.
Okay. How far away is that reality?
Oh, not far. I think, boy, I keep track of it too. I apologize. I want to say that, it puts him up at 64 a crack. I think he's had 10 launches, so he's got about 600, maybe getting close to 1,000. I can't remember the total number, but I would say it's not far away. I would say probably within 2 years. I keep track of space launches and so forth, and I've watched some of that. I don't know it in detail, but I don't think it's far away.
What happens to the expensive infrastructure that providers are building on the ground right now if that becomes a reality?
My understanding of what his vision is to provide coverage in parts of the world where there isn't coverage. I don't know that what he's doing is going to supplant the existing infrastructure. I think his goal is to make it available to everyone. So it's more like the folks that don't have access today.
It probably will be more expensive than land-based.
Yeah, I would imagine so. And I would also suspect the performance is not as good as what 5G is going to evolve into. I mean, it'll be good enough, but I don't know that it's going to, I don't know that you or I would convert to it to say, oh, well, that's a better solution.
Right. Thank you.
Sure.
I have a question.
Yes.
I have an old 5S
Oh, yes.
iPhone, and I'm thinking of upgrading. And I don't know if things keep changing and the technology is better and better, if I should wait and get a new iPhone in 2021. I have Smart Talk, which my husband signed up for, which is through Walmart.
Yes.
It's $45 a month. And I just would like some direction if you're, and I also have Comcast Xfinity here. I don't read on my phone very much. I read on the computer. I use Google Maps and phone calls and texting mostly.
So
Never streaming.
yeah, so what I would tell you is that it would, if you're okay for now, I would wait till next year, because I believe the next, if I were you, I would wait till, if you can, I would wait till the next iPhone comes out that supports 5G. Because if you're running a 5, that means you get the most out of your phone. And so I would say don't upgrade until that technology is available. And if you want to stay with an iPhone, then I would wait till that technology is available. And I suspect it will be available in their next revision.
Thank you.
You bet. It's past 11 o'clock. I don't know, is the Kim?
I have one more question.
Oh, sure.
Could you explain again the difference between broadband and low band?
Oh, low band and the high speed. Yes. So again, if we go back to the electromagnetic spectrum, you've got these waves or oscillations of the electronics in the air, and the slower they are, the slower the data, or the limits are on the amount of data you can move. But the advantage is they go further. They'll go miles. The super fast stuff, that's the high frequency stuff, that can carry a lot of data, but it won't penetrate wall. It won't penetrate a cement wall. It won't penetrate a building very well, and it just doesn't go as far. So it might go 1,000 feet or 3,000 feet or something. And so in order to be able to provide that super high speed capability, the antennas have to be closer, and there have to be more of them. And so that build out's going to take a long time to get that super high speed stuff. The other question you have to ask yourself is, how much do I need it?
I'm listening.
Anyhow, hopefully, does that answer the question?
I think it does, because I'm using an iPad more often than I use the device called a phone.
Yes.
And often it pops up on my screen, your broadband is interrupted. And it's because I live in a concrete condominium, I guess.
Could be.
Yeah.
Coverage is always the challenge. And the carriers deal with it all the time, and we as customers deal with it all the time. So yeah, I'm not surprised.
Okay, thank you.
You're welcome.
Thank you, David. It's 11:05, so I'm going to give everyone permission to go as class time is over. If you need a minute or two to stay on with David, I'm sure he'd be willing to take one more question, but I'm going to stop recording now and give you all the permission to go. Thank you, David, so much. This was awesome and very informative, and we appreciate you doing this course for us today.
Great. Happy to do it.
Thanks.
Thanks very much.